we are starting section 1.5. This section, we've already touched on some of the concepts from this section in the past, so that'll be nice. But this section is going to talk about solution sets of linear systems. And we're going to actually introduce this new concept right in the beginning that's going to be important and it's going to stick with us for the whole quarter. Namely, we would say that a system of linear equations is called homogeneous if it can be written as AX equals 0. This 0 is important. And please note that that's a 0 vector. So such a system always has which solution? So if you just think about it for a moment, what x could we put in where the equation AX equals 0 would be true? Can you tell me an x that would work? From Gerald, 0. Okay, so such a system always has what's called the trivial solution, and namely that the x is equal to the 0. So x equals 0, this is the trivial solution. So we know that every homogeneous equation, AX equals 0, has the trivial solution. That's not very exciting. So the important question is whether or not there is a non-trivial solution. So this phrase right here, non-trivial solution to the homogeneous system or homogeneous equation, you're probably going to hear this phrase 20 times, 50 times, 100 times in this class. Like this particular phrase is going to come up over and over, and all it's saying is are there x's that are not 0 that are solutions to that equation there? So since there's always a trivial solution, there is a non-trivial solution if and only if there is at least one free variable.
What about if there is one row that only has 0?
A row that only has 0 could be okay. The question is, are there free variables? So think about the case where you have 0, 0, 0 here. I'll say this one would be 0, and then this might be 2 and 3. So here, there's a free variable. So this would tell us we could potentially have non-trivial solutions to the homogeneous equation. But imagine that you have a B matrix, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So notice that there's no free variable, even though both A and B have a row of zeros. Did that answer your question, Hui?
Yes, pretty much.
So again, just to be clear, in this case, there would be non-trivial solutions to the homogeneous equation. And then in the other side, here there would be no non-trivial solutions. Back to the examples. So I want to determine whether the following has a non-trivial solution. If so, I want to describe the solution set. So the first thing I'm going to do is I'm going to write this down as an augmented matrix. And if you could pull out your text and friends and row reduce for me, that would be nice. When we want to show that matrices are row equivalent, like they're not the same matrix, but they're the same matrix after row operations, we're going to use the little tilde. Row equivalent. I think I did not do this the one other time this has come up. I've got from Ahmed on the first row, I've got 1, 0, and then 2.125. I think that's, yes, a 2.125, and then 0, 1 minus 0.75, 0, 0, 0, and then 0, 0. One thing you'll note is that if you're doing, if you're solving a homogeneous system, the zeros on the right side are always just going to stay zeros. Nothing is going to change there. Those are always the same. Let's see. So what does this mean? We want to determine whether the following system has a non-trivial solution. So is it going to have a non-trivial solution? Yes or no? And how do we know? So I've got one yes. I got yeses from Gerline and Felix and David and Elijah. And from Richard, because it has a free variable. Non-trivial solution, yes, because there's a free variable. And we know there's the free variable because you have the column without a pivot in it. Okay. So then the second part of the question says, if there's an infinite number of solutions, if there's a non-trivial solution, then we want to describe it. So now we're going to come through and we're going to try to explain what this means. If so, describe the solution set. So to describe the solution set, we're going to go from here. We look at the row reduced form and we got to figure out what does that mean. So that tells us that x1 equals negative 2.125. Negative 2.125, that would be 17 over 8. And that is x3. And x2 is going to equal 3 over 4 x3. And x3 is free. So if we put this together, we could say that x, which is the same as x1, x2, x3, would be equal to x3 times negative 17 over 8, 3 over 4, and 1. Notice this one being free is going to match with that one right there. And so this would describe this thing that we found here. This is describing all solutions from Andrew. It's free, so it can be anything, right? Correct. Yeah. But what we have here is this is all non-trivial solutions to the homogeneous equation. Got a question from Ratana. Why is x3 equal to 1? It's from, you could think about this line as saying that x3 equals 1 x3. From Ahmed, since ax equals 0, does this mean that a times 0 equals x? 0 is one solution. That's the trivial solution. And you could get that, in this case, if you let x3 equal 0. But the thing that's important is, are there solutions that are not 0? So these are all solutions that are, this gives you all the solutions that are not 0, as well as that trivial one.
Dusty, so we answered the question by doing the row reduce, right?
Mm-hmm.
Yeah. Why did we do the second part where we have the new matrix where that you show the all non-trivial solution to the ax is equal to 0?
Right here, down at the bottom, this part right here.
Yeah, that part.
Because what I'm trying to do is I'm trying to describe, it says, if so, describe the solution set. So this is that solution set.
Oh, so that's how you should describe it?
That's how you would describe it.
Oh, all right. Thank you.
Yeah. So describe all solutions of the homogeneous system 3x minus 3x1 minus 4x2 plus 5x3 equals 0. And so this is a kind of boring, you can have like a boring matrix. So we could write this as 3 minus 4, 5, 0, like that. And you could dump this into your calculator, but don't overthink. We could just divide everything by 3. 1 minus 4 over 3, 5 over 3, and 0 again. And so what does this mean? This is telling us that x1 is equal to 4 over 3 x2 minus 5 over 3 x3. x2 equals x2, it's free. and the x3 is also free. So we can put this stuff together to describe all solutions by saying that x is equal to x1, x2, x3. But in this case, you'd have x2 times 4/3, 1, 0, plus x3 times minus 5/3, 0, 1. All right, so what's important about this particular thing is that it creates a connection from set chat we could have. I just didn't have space. This x right here is, that x is just x1, x2, x3. So this connects a little bit with Calc 3, Calc 4 with planes. So you can think about this vector here as being like a u vector, and this vector here, the second one, not wanting to highlight, sorry, that one right there being like a v vector. And so your u's are giving you stuff along this axis line, and your v's are giving you stuff along that line, and the plane is everything between them. Thank you, Harpreet. That's correct. You could think about your x in this case as also being like x2u plus x3v. Or if you will, maybe it would look a little bit more familiar if you use parameters like s and t. So this is all equal to x. So what this would give you is it's like a parametric equation for a plane. I think I'm a little bit ahead of myself. I think this is described below right here. So the previous example demonstrates how we can write solutions to in parametric vector form. So you have x equal to su plus tv. So again, this is the parametric equation of a plane. It's kind of a Calc 3, Calc 4 thing. And in particular, one thing I want to point out about this particular plane is that this plane goes through the origin. Because if you let s equals 0 and t equals 0, then x will be 0. It's the trivial solution. In example 3, we're going to do the same thing, and we'll start by row reducing. So we take our system, here's our A and our B, from AX equals B, and we could write this as an augmented matrix. And if you guys are on fire, if you could enter this in your calculator and give me the row reduced form, that would be cool. And if you don't know how to use your calculator for this, please ask me before or after class. Okay, I've got from Felix, thank you. 1, 0, -5, -2. 0, 1, 2, 1, 0, 0, 0, 0. Like that. So we do have a free variable in this case. They're in x3. And so let's make sure that we're tracking what this means. So we're trying to write down our solution set. So this is telling us that x1 is equal to -2 plus 5x3. And x2 is equal to 1 minus 2x3. And x3 is equal to x3. That's the one that's free. Okay. I know sometimes this trips people up. Notice here you have a minus and there you have a plus. How come it was minus in one place and then plus in the next?
You added it to both sides?
Exactly. Thank you very much. So I added the negative 5x3 to both sides. So now we can put this stuff together. So this is telling us that x, which is, since you guys were wanting to see it this way, x1, x2, x3, you don't have to write this, is x3, and then it's the coefficients, the negative 2, 1, 0, plus x3 times 5 minus 2 and 1. Again, the free variable will line up with a 1. So you could write this, if you will, as x equals p plus t v. And so in this particular case, the p is this vector here. Okay. And then the v is, so I'm looking for a color I haven't used yet. And here's the v. So we can visualize this as follows. So to visualize the solution set of ax equals b geometrically, you can think of vector addition as a translation. So what we're saying is that this line right here is all the solutions to the homogeneous, the non-trivial solutions to the homogeneous equation. And then we have a translation, and our translation would be P. Actually, let me change my color scheme, sorry. By P, and this whole thing would give us the something along. There's a little, it's not perfect, but this gives you a little bit of an idea of what's going on. This orange is the same. So go ahead.
Can I ask a question? So the vector next to the vector you just highlighted orange says P plus TV.
Mm-hmm.
Does that mean that is the one that's equal to X?
Yeah, X is equal to P plus TV.
Okay, so my question is, you highlighted a line on the left side and then you highlighted X with yellow. Are you trying to say that that highlighted line is X, or because what I'm seeing is the vector that's connecting the dotted vector is the one that says P plus TV. So wouldn't that be the X vector?
I think the yellow vector here represents your X's, and in order to represents the X's, and you could get it by taking the orange one and adding the orange and pink, like orange plus pink equals yellow.
Okay.
Did that answer your question?
Yes.
From Ahmed, so the value of t doesn't matter. T is a parameter, and so if you pick a specific value of t, it will give you a point on the line. If you let t have all values, then it would give you the full line. This is a really weird way of writing it, but this is like a Calc 3 thing. Maybe I can write it that way. So in Calc 3, you might have had like r of t equals x naught plus at, y naught plus bt, z naught plus ct, something like that. And so in this particular case, these guys are your orange P, and A, B, and C are your V vector, and the T is the same. I don't know what color that is. T is the same. And this R is the same as Rx. There's the connection between here's Math 220, here's Math 163. So the solution set of AX equals B, so this is sort of like trying to conclude it, is a line through P that's parallel to the solution set of ax equals b, or equals 0. And here, it's not always going to be a line. It's a line if there's one free variable. Let's wrap this up with one little teeny proof, and then we'll call it a day. So if 2, it would be a plane, or a plane in however many dimensions, et cetera, et cetera. Yep, that's correct. So suppose the equation ax equals b is consistent for some given b, and let p be a solution. Then the solution set of ax equals b is a set of all vectors of the form w equals p plus vh. This is what we were just talking about, but it's now more general. So claim the first part of theorem 6. Suppose that p is a solution of ax equals b, so that AP equals B. If VH is any solution to the homogeneous equation AX equals 0 and W equals P plus VH, then W is a solution of AX equals B. So I've already written the claim. We got these 3 parts that we have to work with. Next, we've already got the claim, so next we'll do our proof. And then we've got to do our let. And at first, we don't really know what to put for our let. So we kind of look up above and we think about all these terms. Let's see, what do we have to, we've got A's, P's, B's, and some sort of like VH thing. All of these things are unknown. And so I'll tell you a secret, saves you some writing. So we can say let A, B, P, and VH be as given above. It's a little bit of a shortcut way of saving yourself some writing. You're like, oh, I don't want to write all those things again. All right, we need some sort of a W. So if W equals, what's our W going to be? W is going to be P plus VH. P plus VH. This implies that AW, we want to show, remember, we're trying to show that AW is a solution, or the W is a solution. W is a solution. So if we're trying to show that W is a solution, we're going to try to show that AW equals B. Here's my AW. And we'll be done in just a moment. So this would be the same thing as A times P plus VH. One of our things from yesterday said we can split this up to be AP plus AVH. What's AP equal to? Yeah, so we have AP equals B. And then what's AVH equal to? AVH is a solution to the homogeneous equation. So this one must be 0. So this whole thing is equal to just B. So therefore, we can state our conclusion, 3 dots. Therefore, we have that W is a solution to AX equals B, which is what we were trying to show. So we are picking up where we left off yesterday, talking about solution sets of linear equations. And this beginning is simply outlining a process for writing a solution set. So we've been doing this, but you might be saying, hey, I don't know what's going on. I just sort of need a summary of what's the process. And so our process is pretty straightforward. The first thing we do is you row reduce. The next thing you do is you're going to write things in terms of the free variable. The next thing you do is you write that typical solution of X as a vector. And then lastly, you decompose X into linear combinations of vectors. And we've done this a whole bunch of times, and I think we've got another example to follow in just a moment. All right, let's keep going. I decided to save a little bit of work and did the first couple of steps here myself. So each of the following equations determines a plane in R3. Do the 2 planes intersect? If so, describe their intersection. And so here's that step 1. I take my system, write it as an augmented matrix, and then we're going to row reduce, just like we said before. So then step 2 is that we need to express each basic variable in terms of any free variables appearing in the equation. And so we got to figure out what this means. So this is telling us that x1 plus 3x3 equals 4. Still do not understand what's going on here. x2 minus 2x3 equals -1. So here's my step 2, where I have expressed the basic variables in terms of any free variables. I guess I should also write that x3 is free. So step 3 is I'm going to write a typical solution x as a vector whose entries depend on the free variables. So it's like step 2. Step 3. Think about it like saying that your x, which is x1, x2, x3, is going to be like 4 minus 3x3 minus 1 plus 2x3 and x3. And then the last step is to decompose that x into a linear combination of vectors with numeric entries using the free variable as a parameter. And so we have that our x is equal to 4 minus 1, 0, plus x3, here's the parameter, times -3, -1, 1. Like we talked about yesterday, that 1 corresponds with this x3, which was our free variable. Y -1, 2. We did this in class a couple of times yesterday. If you want to write it as step 1, step 2, step 3, step 4, great. If you want to combine steps, that's fine. But we are doing, each time we are really doing all 4 of these steps, even if we don't write them. Some of them we're doing in our head. Next question is almost the same. And what I want to point out here is just kind of the connection between things. Oh, actually, let me go back to this previous one and make a connection again. So you might ask, what did we just do? So like if you wanted to visualize this, this is a line and it goes through the point, through point 4, -1, 0. And it is in the direction of -3, 2, 1. Yeah, so the question asked, I lost part of the directions. The question asked, do the two planes intersect? The two planes do intersect, yes. And they intersect along this line. Got a question from Sunghoon. How do I go from step 3 to step 4? I'm separating things out. These guys right here are here. And these guys here. There's my x3. And the coefficients, let me see if I can change my color a little bit. And the coefficients, -3, 2, and 1 are right here. So back on example 5, so I want to write the general solution. So again, I've row reduced, that was my step 1. Step 2 is going to be to write this as x1 minus 0.3 x2. Oh my gosh. Minus 0.2 x3 equals 7 or equals 0.7. And then we have x2 is free, x3 is free. So then step 3 would be to write this as a vector x. So you can think about your x as being x1, x2, x3, and it's equal to, you can think about it like a 0.7 plus 0.3 x2 plus 0.2 x3 And then from there, we can split it up into kind of the components. So we're saying that our x is equal to 0.700 plus x2 times 0.310 plus x3 times 0.201. And what you will notice here is that there's one column. So you have a free variable here in x2, and that's going to correlate to one of these columns. And then you have a second free variable in x3, and that's going to correlate to another column. So you can have as many columns over here as you do free variables. And you might say, we didn't, good question from Evan, why did we initially divide by 10? We didn't have to divide by 10, but I divided by 10 so I could just keep my process the same each time. By dividing by 10, I was able to end up in reduced row echelon form. But you could have done it the other way as well. So again, just so you're tracking what this means. So our interpretation. Oops. So what this is, there's two vectors, two linearly independent vectors, the yellow one and the blue one. And so this will be a plane through, there's my famous word, through the point 0.700, and that includes vectors 0.310 and 0.201. A notational note here, I'm using the angle brackets for my vectors, and the only reason I'm using the angle brackets is because that's what most of you probably used in calculus. And so I figure it's easier for you to visualize things at least 2 weeks into linear algebra if I write it in the old notation than if I keep it in the new notation. So these vectors are the same thing. It's just old notation versus new notation. From Andrew, is it a plane because of two free variables? Yes, we're in 3 dimensions. So we're in 3 dimensions and we have 2 free variables. So we're going to generate a plane. Yeah. I'm not going to finish the next question in its entirety, but I want to at least start. Every free variable will have a column in our final result. Believe it or not, I'm not super proud of this, but I am a mathematician with my degree in math, and I've never taken a chem class in high school or in college. 256, Abe. That was a joke, a computer joke. Yeah, there's no limit. For linear algebra, for vectors, they have to be of finite dimension. I think you can do infinite dimension with things called maybe like Hilbert spaces and stuff like that, but I've never studied that. So for those of you that have had chem, which I would assume is just about everybody else in the room other than me, you've done this thing where you're balancing equations, and we thought we'd just look at it from a linear algebra perspective. So here, what are we doing? We're taking some propane right here, and we're combining it with some oxygen here. And then after chemical magic happens, it forms CO2 here, plus, what do we have? Plus some water here, right? So that's kind of the way the chemical reaction works. And so if we were to think about this from a math perspective, we're saying that if you have x1 of 380 And here the 3 is representing the number of carbons, the 8 is representing the number of hydrogens, the zeros representing representing the number of oxygens. Oh, I feel so much better knowing that some of you also are chem deficient. So I'm not the only one that's ignorant. So O2 would be 0 hydrogens, 0 carbons, 0 carbons, 0 hydrogens, and 2 oxygens. And because we want this to balance, we will have an equals, and it's going to equal some amount of CO2, 1 carbon, no hydrogens, 2 oxygens, plus some amount of H2O, water, 0 carbons, 2 hydrogens, 1 oxygen, like that. I think it's just, I don't know, Croy. Yeah, I can't answer the question other than that it gives you a way of, perhaps a way of thinking about what we're doing in linear algebra and or what you're doing in chemistry, kind of from another framework. So what this is telling you is that you have X1 380. Well, let me make sure you're tracking. So I think everybody sees it. So plus X2 002 minus, because we have to move everything to the other side, X3 102 minus X4 021 equals 000. So we could turn this thing into a system. So we need to solve the augmented matrix. It looks like 380 002 -1 0 -2 0 -2 -1 and 0 0 0. Yeah, I'm not planning on doing this by hand. Twee. Yeah. So then now at this stage, we can just dump this thing into our calculator. And you're going to get some identity matrix looking type of thing. And then -1. I guess I am doing the whole thing because it's interesting. Oops, this is 1. What? No. This is using your. Don't feel like you're cheating, Richard. This would be like mad science skills or mad math skills. The chemists would all be proud of you, or at least your math teachers will be proud of you if you do this in chem class. So let's think about what this is meaning. This is telling you that your X is equal to, it's going to be an X4 times 1/4, 5/4, 3/4, and 1. And notice that we could multiply this by 4 and the numbers will be a lot nicer. So this is telling us, so our interpretation is that we have, I'm trying to remember what's what. What is C3H8? Is that propane, I think? So you have 1 C3H8 propane plus 5 oxygens equals, or goes to 3 carbon dioxides plus 4 waters. away. Trying to find my colors up above. Oh my gosh. So one question for you. Where did the 1, 5, 3, and 4 come from? Yeah, from Ahmed and others. I'm looking at this X vector and I'm saying I'm not going to include a fractional amount of some molecule, like a fourth of a molecule. I'll do 4 times that or 1 full propane molecule. And so I just found the multiply by the least common denominator, and it works. So questions about that? Is this chemist suicide, or would this save you in chemistry? I don't know. Cool. No extra charge for this example. So cool. All right. Any other questions? Why are there 4 rows rather than 3 rows? Kyle has a good question. Kyle's question is, why are there 4 rows rather than 3 rows? So I think what he's saying is, why are there 4 rows in X? And so, so you can think about what do the rows represent here? Here the rows are the types of atoms. Atoms, carbons, hydrogens, oxygens, right? Whereas in X, the rows represent the number of each molecule, or the and if it helps, you can think about the combining equation. If we kind of go back to where we started, we're saying that we have A times X equals 0. Like that's what we're starting with. So our A matrix is 3 by 4. Our X vector is 4 by 1. The middle dimensions match, and our result is going to be 3 by 1. Yeah, X4 is free. Yeah. Questions? Good questions so far. Other questions, comments?
Sorry.
Go ahead.
Can you explain the second from the last part? X equals to X4.
Right here?
Yeah.
So I skipped a step, but the step, for example, this particular step I would have written as x1 minus 1/4 x4 equals 0. And then I can take this guy right here and shift it to the other side.
Okay.
And there it is.
Got it. Thanks.
Good question.